Hi there! For this video, we are going to show that the counting measure is really a measure. Hence, we'll be using here the definition of the counting measure and check whether the two conditions for a certain function to be called a measure is applicable to the counting measure itself. Take note that for this given counting measure, we were able to discuss and illustrate it earlier in the previous video. I'm going to automatically write here its definition. We have here the mu of a, where a is a subset of x or an element of the power set of x. We have here this piecewise function stating that its value is positive infinity if a is infinite, while it is the cardinality of your a if a is finite. So we're going to show that this is really a measure, and hence it's called counting measure, using the definition of a measure function. And for a measure function, of course, we need to identify or satisfy these two conditions. I'm not going to write here as well the definition of measure function, or I will write it here. Let's say this is the definition of a measure: a function mu, okay, with mapping, let me rewrite it here, sorry for that, a function here for a while, mu with mapping to the script m into this interval 0 to positive infinity, okay, where m, or the script m, is a sigma algebra, okay, is a measure if it satisfies the following. Okay, the first one is the first condition is that the mu of your empty set is 0. Okay, and the second is we have here if we have a set of a sub I for I be natural numbers, is a disjoint, disjoint collection, collection of sets in your script m, then we are going to show that the mu of the union of all a sub I, where I starts from 1 to infinity, is just equal to the summation of the measure of each a sub I for I starts from 1 to infinity. So these two should be satisfied, this first property and second property, using this definition here for a counting measure. Again, the complete definition is already available in our previous video, and we also have this portion in our definition, so I'm not going to show it anymore here. You may want to review that. So here comes the proof. We will start with the first condition. Okay, so we have here the proof. We need to show that the function or mu of your empty set is 0. Now, looking into this, which of these two would satisfy the empty set? Take note that since empty set, okay, is finite, then we are going to use its cardinality. And let's find out if the cardinality is 0. Okay, then the mu of empty set is equal to the cardinality of your empty set. And what is the cardinality of the empty set? It's actually 0. So with this, we have shown already our first condition where the mu of our empty set is equal to 0. So that's very clear for this part here. So you can also label here 1 if you would like to. Now, for the second portion, we need to show that if our set a sub I is a disjoint collection of sets, meaning there are no common elements for whatever a sub I are, we can show this relationship. But take note that in this situation, it's a counting measure. At the same time, we have here I which is an element of natural numbers, and natural numbers is infinite. So there are possibilities or cases to illustrate this, and all the cases must be satisfied in order for us to say that our second condition is met. The first case is, what if our a sub I is infinite, or a sub another sub variable later and we're going to use. Second is, what if it's finite? Okay, where part of finite relationship is the idea that our it's finite but it's not empty, or a sub i's are not empty. Okay, so let's try to look into the first case. But before we go to that, let us introduce this portion here as part of our proof. So let's just have here a second 2. Okay, we're going to have here let. So this would appear set a sub I for I element of natural numbers be a pairwise disjoint. You can already use here the term pairwise disjoint sets in script M. Okay, so we might not see here script M again. It's already presented our definition here. Now once we were able that, let's talk about case 1. Case 1 is what if there exists a certain k which is a natural number such that our a sub k is infinite. Okay, because our a subs are actually subsets of a real numbers, and what if it's infinite? Okay, so we need to show that this is true for situation like that. That would mean then using this here, we can construct this illustration. The union of your a sub i's, where I from 1 to infinity is infinite as well. Okay, because what if it's infinite, right? If it's infinite, take note that in our definition we'll be using this here. Okay, so we are going to show that this is true for this as well here, because the mu of this, we're going to show here then the mu of this, where I starts from 1 to infinity, since it's infinite, based on the definition, is positive infinity. We need to show that this portion here is also positive infinity, so that they are equal, because this should be established for this case. Okay, so what if we have something like this? I would like you to consider here, okay, consider here mu of a sub k being infinite plus another summation of mu of a sub I for I is not equal to k, meaning this is separate to that. Okay, so this will run until whatever the value of I except for k, because k here is already given here. Take note that this is also equal to the mu of the union of a sub I, where I says 1 to infinity, okay, which is identified as positive infinity earlier. We need to show this is also positive infinity, being the what you separate two forms of this, because as we take here, as we remove certain k, we will have here the mu of k, because this is the union, or this what you call this one, summation, or this is equal, right? This is, they must be equal to one another. Now what is the mu of a sub k? Being a sub k is already infinite. Okay, infinite. This would mean this here is positive infinity. Okay, that's infinite. Now plus the summation of the union of a sub I, where I is not equal to k. Now whatever be the result of this, take note, you are adding this to infinity. Okay, you're adding this to infinity. By the way, this is still question mark. That's what we're going to show. So you can actually separate it here. So you will have then, okay, as part of our illustration. So since we are adding infinity to this, and whatever be the result of this, this will also equal to infinity. Okay? Hence, we were able to establish by the combination Okay, since the mu of a sub k plus the summation of the mu of a sub I, where I is not equal to k, meaning they are separate, this is just equal to the summation of mu of a sub I for all I 1 to infinity, which includes k and the non-k's. This is positive infinity. We have established that from here, asterisk and double asterisk here, that this expression is just equal to this expression being positive infinity. You will have here, hence, the mu of the union of a sub I, where I starts from 1 to infinity, is just equal to the summation of all mu of a sub I, where I starts from 1 to infinity, which is positive infinity. So this is this states that case 1, okay, 1 is satisfied. Okay, that's the first thing. That's the first case, because not all a sub i's or a sub k's are infinite. Okay, let me use another portion here, another page. Hopefully you're following. Let me add, okay, something like that here. We will talk about case 2. We're able to establish that when a sub k being infinite or is satisfying the second situation, okay, we were able to show that this is true. The mu of union of a sub I, where I starts from 1 to infinity, is equal to the summation of all mu sub a sub I, that's mu, where I starts from 1 to infinity. Pardon with that, this is already presented here as well. Okay, so what if in case 2, what if a sub I is finite? Okay, and for all I element of n. So if it's finite, take that there are two cases for finite sets. Okay, so we'll have here subcase 1, okay, or subcase I, where the finite set is not empty. Okay, finite set rather is not empty. And later on, the second subcase for, because there are two situations for finite sets. Finite sets is empty because empty is a finite set, and those non-empty sets. This is the subcase number 1, because we have to establish the second condition for finite and infinite rather in finite situations. And again, finite situations has two portions. So we'll have here this first part. So with this, since it's finite, take note, this is the definition, and of course we'll be using this definition as this is the definition for the counting, right? Counting a measure. So this should be the goal. Okay, so again, the first one, this is satisfied already. Okay, for what they call this one, situations for infinity, but of course we're going to look into the finite a sub i's. Okay, so then we will have here the mu of a sub I, okay, is equal to the cardinality of a sub I, right? Let me separate this, okay, because a sub I is finite. I will be using this second here, which is actually greater than 0, because the cardinality will only be 0 if we consider empty set. But since we are considering here the non-empty sets, so they are all greater than 0 for all I which are integers. Hence, okay, if that would be the case, the summation of the mu of a sub I, okay, as I starts from 1 to infinity, since our a sub I is greater than 0 and there are infinitely many, okay, when we say greater than 0, it could be infinite, right? So this is still positive infinity. Okay, the reason for that is this situation here, the cardinality doesn't have any specific value, and it's actually greater than 0. And take note that a sub I can take any possible value, positive value, and we don't know what is that, so that's a positive infinity. So take note of this. Okay, so we will have this take note, we're going to show that they are equality, so we will be introducing this portion now. Okay, so now according to action of choice rather, that's why we also presented that a while ago in a previous video. By action of choice, okay, there exists a certain E which is a subset of the union of A sub I, so that this will reappear, okay, where I starts from 1 to infinity, such that, okay, the intersection of E and any A sub I is a singleton set for all I element of integers. Okay, so actually this is by axiom of choice. You might want to review that on a specific video also discussing the axiom of choice. Why do we need this? Because once we're able to introduce this, we're going to look into the idea that this implies that E is also an infinite set. Why is that so? Even if E is a subset of A sub I here, where I starts from 1 to infinity, we know that A sub I is just non-empty. So it could take any what they call this one, any value of its cardinality and such, like this is its definition here. So with that, since it's an infinite set, hence the union of A sub i's, where I starts from 1 to infinity, is also infinite. Okay? And if that would be the case, thus, the mu of the union of A sub I, where I starts from 1 to infinity, since it's infinite, we'll be using the second statement, the first statement here. Okay? Even if A sub I is finite, okay, it talks about the idea that by axiom of choice, this is actually a subset of all of this. But since E intersection A sub I is a singleton set for any I not an integer, so it can be considered that E is infinite set. This is also positive infinity. Now looking into that and this portion here, okay, thus we were able to establish for this subcase that the summation of the mu of A sub I, where I starts from 1 to infinity, is just equal to the mu of the union of A sub i's, where I starts from 1 to infinity, is also positive infinity. So the subcase 1 is already okay. How about subcase 2? Still, A sub I is finite, but, okay, there exist n elements of your set of natural numbers such that A sub n is empty set for all n, this is capital N, by the way, element of your capital N. Okay, so this is the first one. A sub 1 is finite, but we have infinitely many finite sets. And now here, we're only specific to our finite set. Now, take note, for this case, it is enough to consider two sets. Say, A sub 1 and A sub 2. Okay? Thus, we know that the mu of A sub 1 union of A sub 2 can be represented as mu of A sub 1 plus mu of A sub 2. Therefore, with this now is actually a shorter or a expanded form of the summation of mu from A sub I, where I starts from 1, that's 1 rather, 1 to 2. So this actually looks like this summation, which could work for all. And this, the union, is also looking into this. They are now equal to one another. Because if our A sub n is empty, that would mean this is empty, union empty, right? Okay? The union of empty is empty, and the mu of empty is 0. Now the mu of empty here is also 0 plus 0. They're also equal to one another. So with now here, therefore, with this case 2 are also satisfied for this situation, and case sub case 2, and then case 1 already satisfied earlier for infinity, and for finite there are two subcases. Subcase 1 where it's a sub I is finite but non-empty, and when it is empty, we're able to establish the two relationship already, saying that the mu rather of all union of a sub I where I starts from 1 to infinity is equal to the summation of the mu of a sub I where I starts from 1 to infinity. Therefore, since the two conditions for being a function to become a measure is satisfied, therefore our mu here is a measure function. Don't worry, this is just a proof that counting measure is really a measure. Okay, and we were able to illustrate already the counting measure in a specific video, but this is just the proof. This is to show that the counting measure defined as this definition satisfies the two conditions for a measure function. We'll have another video for proving whether a measure, certain measure is a measure, or that is actually for the Dirac's measure, and we'll have that on a separate video right after illustrating what is the Dirac's measure. Thank you very much for watching.